Hello, everyone. Welcome to another episode of Q&A about future, of science and technology. Uh, let's see. All kinds of questions come in here. Well, I see one from Vivi asking what my opinion is about photonic computing. Well, the thing that's kind of worked for a long time is using electrons as kind of the carriers of computational information in the devices we set up. I think they're not the only possible solution. I mean, at this point, if you ask sort of how many electrons represent one bit of information, it's, I don't know, somewhere between 10,000 and 100,000 per bit, so to speak. And as sort of one is going on kind of making and the typical technology of computers is semiconductors and channels that have been etched out of semiconductors, and those channels are getting smaller and smaller. I mean, the precise widths of the channels are a little bit difficult to define, but 5 nanometers is kind of the aspirational state of the art these days. And the typical size of an atom is on the order of let's see, it's on the order of an angstrom, which is 1/10 of a nanometer. So we're talking about sort of widths of wires, effectively, of order tens of atoms. And when they're that narrow, there are all kinds of effects that are essentially quantum mechanical effects and so on that start coming in. I think the traditional way of doing computing has been you use electrons traveling in these kind of wire-like kind of things etched out of semiconductor. Now, can one do something different from that? Yes, one could use photons instead of electrons, and one could have those be in kind of channels that have been etched in something too. The difference is in the case of a sort of an etching a wire out of a semiconductor, you do that by doping the semiconductor to change its electrical conductivity. In the case of making a channel for a photon, you'll be more making a channel where you have a different refractive index for the photon, so that it gets kept in that kind of photon wire, so to speak. That's kind of the I would say that's sort of at some level the comparison. Now, what can one do with photons that one can't do with electrons? Well, there are some effects that sort of will work better with photons. There's some things that are more difficult to do with photons than with electrons. I mean, a photon is something where, in order to detect typically when you read out the data from your computer, you want to read it out with electrical wires. So you've got to convert whatever is going on to an electrical signal. That's not very difficult to do, because there are plenty of, in semiconductors, you can have something where photon comes in, electron goes out. Kind of that's a generalization of the kind of photoelectric effect, the thing that originally made it clear that photons exist back in 1905 or something. But there are also things that one can potentially do with photons that one doesn't so readily do with electrons, that have to do with the interference of light. So one thing is just to have photons instead of electrons kind of going through wire-like things. Another is to do things that involve interference of light. Now, there's one I should have said, there's one critical thing to think about there, which is in the case of electrons going through wires, the thing that really made that work was the invention of switches for electrons, namely transistors. And in a semiconductor, for example, it's rather easy to make a field effect transistor where essentially you have electrons going along in a wire, or it's not really a wire, it's one of these etched kind of channels. And then when you have another etched channel that's going sort of at 90 degrees to that, and you use different kinds of doping in these different channels, you can have something where when there is a voltage applied to that gate, the thing that's sort of going across the channel, it affects whether current can pass whether electrons can pass through that gate or not. And so by changing what's at the gate, the voltage at the gate, you're switching whether current can go through the wire. And so when you sort of invert that process, you can essentially have an amplifier because you've got this big current that's trying to go through. You've got this little effect on the gate. And so that little effect on the gate is kind of leveraging this big effect in what's happening in the wire, so to speak. So it's a very nonlinear effect. It's not something where you're just sort of combining this number of electrons plus that number of electrons equals the numerical sum of that number of electrons. It's something where you are switching sort of nonlinearly. A small effect here causes large effect on the current that's passing from the source to the drain in the field effect transistor. And a typical modern microprocessor might have billions of field effect transistors in it that are forming the whole circuit needed for the microprocessor. Okay, so the big thing one would really love to have is a photonic switch. It's something that does that kind of thing, but for photons rather than electrons. We don't know how to make such a thing yet. There are sort of ways to get a little bit close to it by using nonlinear optical elements. So let me explain a couple of things here. So when you're dealing with light, you have a certain intensity of light. You also, but you can think of that light as being, well, if you can think of the light as being this wave. It is literally a kind of a thing where the amplitude of electric field and the amplitude of magnetic field are varying at the frequency corresponding to the frequency of the light. In the case of light, that is around, let's see, 10 to the 15. Right? Yeah, I think that's right. Is it 10 to the 15 or 10 to the 12? I have to work it out. Let's see. A typical light might be 500 nanometer wavelength. That's 5 times 10 to the minus 7 meters. And the speed of light is 3 times 10 to the 8 meters per second. And so we're trying to work out what frequency. So it's 10 to the minus 7 divided by 10 to the 8 is, yes, I was right. It's 10 to the 15. That's what I thought. So it's a 1,000 trillionth of a second is the time interval between the peaks of the wave for that's forming the light. So I mean, light is this configuration of the electromagnetic field that involves the electric field increasing, decreasing, increasing, decreasing, as we just worked out 1,000 trillion times a second in the case of visible light, and the magnetic field doing the same thing. And turns out the way the equations of the electromagnetic field work, when you have that combination of electric field variation and magnetic field variation, the result is that you have a traveling wave that moves at the speed of light in a certain direction. And the thing that is sort of a very fundamental feature of the equations of electromagnetic field is that if you have two electromagnetic waves or two configurations of the electromagnetic field, you can just add them together. There is a way to make, if you have something that makes a certain kind of electromagnetic wave, and another thing that makes another electromagnetic wave, then there is a thing that will make those two electromagnetic waves combine together by just taking the kind of linear sum of the electric amplitude, the amplitude of the electric field, the amplitude of the magnetic field. So it's a linear system. You can kind of add light waves together. That doesn't mean that the intensity of the light gets added together, because the intensity is, it ignores whether you've got positive or negative electric field, and it's just taking it's taking the modulus squared of the electric field strength, and that gives the intensity. And it's not obvious when you have two waves, you can end up with, for example, destructive interference, where the waves are out of phase, and where when one wave is positive, the other wave is negative, and so the result is something close to zero, and then the intensity is also zero. So the intensity doesn't add linearly, but the amplitude of the wave adds linearly. And that's a fundamental feature of light, is that it's something where you can add up you can add up amplitudes linearly. That's not true of everything. For example, when you're dealing with gravitational waves, at least fairly intense ones, they don't add linearly. The gravitational wave, if you've got sources of gravitational waves, you can't just say, oh, we got one source that's this, another source that's this. You can add them together, or you can double the intensity, the strength of the source, and you get double the gravitational wave. It doesn't work like that, because gravity is, in a sense, a source of the presence of a gravitational wave corresponds to a certain amount of energy, which itself is a source of gravity. The point is that an electromagnetic wave, the sort of source for an electromagnetic wave is moving electric charges, but the electromagnetic wave itself has no electric charge in it. So the electromagnetic wave itself is just a thing that's produced by those electric charges, and the wave can be added linearly. That's an important feature. It's a good feature for many purposes. It's a bad feature if you're trying to make sort of a computational device out of pure light, because when you have that linear combination of things, that doesn't give you kind of the wherewithal that you need to make a switch. To make a switch, you need something nonlinear, where even though you make, for example, a small change in one thing, it have a bigger change in another thing, it doesn't just correspond to adding numbers together. So the way that things work with light, there are effects where you can, when light is in the vacuum, it perfectly adds up in the way that I've described. When light goes through a material, you can have things happen where the effects on the material cause different things to happen to light that's going through the material. So the most obvious feature are so-called saturable absorbers, where light is being, you're shining light on a material, and that material is absorbing light, in the sense that the atoms in that material, when light is absorbed, what happens is that the electrons in the atoms in the material go from a lower energy state to a higher energy state as they absorb a photon, and then maybe later on they decay again and go down to the lower energy state and emit a photon. In fact, whenever light goes through a material, what's happening is that atoms are absorbing photons and re-emitting photons, and they do that pretty quickly. If they did that in zero time, the light would go through the material at the same speed it goes through a vacuum. But there's a small delay, and the delay depends on the material, and that delay is why light effectively goes slower in a material like water, for example. It goes 1.3 times slower in water than a vacuum, or in glass, maybe about 1.5 times slower than the vacuum. And that's basically because there is this delay in atoms re-emitting the photons that they absorbed. So what can happen is, if you have a high intensity of light, you can end up in a situation where sort of you've filled up all the ways to absorb and sort of transmit along, to absorb photons. And so you'll end up with a situation where, for example, the photons will no longer be absorbed by things, and the material will behave as if it's more transparent. That's one effect. There are other effects. Another effect is that you will get a photon is absorbed at one frequency and then is emitted at different frequencies. So you can end up with, you might have blue light going into a material and then red light coming out of the material, because the blue light, which is a higher energy photon, gets absorbed and then gets re-emitted as two separate photons as the electron energy is turned back into photons, but it isn't turned back into quite the same photons. So there are effects like these. And the question is whether you can sort of arrange those effects to get something which corresponds to something like a photonic switch. And the only ways those effects seem to manifest involve quite high intensities of light, not just individual photons or individual sort of groups of 100 photons or something, rather one's dealing with much larger intensities, one sort of got to get a photon to interact with every one of the atoms in this piece of material or something, which doesn't get to happen when you have that small number of photons. So that's, I think, one of the limiting factors in really having optical computing take off, is having sort of the analog of a transistor for optics. Now, there are other things you can do with optics that you don't get to do with electrons, at least not so easily. The main thing is that because the photons can be thought of as corresponding to waves, you can do things like look at interference between waves. So you can have something where there can be an effect that is just determined by the sort of bulk interference between waves. And what I mean by that is, for example, let's say you're dealing with another kind of wave, let's say the ripples on the surface of a pond or something, and you drop one stone into the pond, you'll see a circular arrangement of ripples coming out from that stone. If you drop two stones into the pond at the same time, you'll see ripples from one stone and they'll go out, and ripples from the other stone will go out. And eventually, when the ripples meet, you'll see sort of an interference between those patterns of ripples, and you'll see these places where the ripples are sort of in phase, and they kind of and the ripples from the two different stones kind of add up, and you get a taller ripple, and other places where they're out of phase, and the ripples from the two stones cancel out, and you'll get sort of it'll be flat in that place. So that phenomenon is something that happens also with photons, and you can get that kind of interference effect, and that's something which happens in a sense that's a different kind of physical effect than any of the ones that's used in something like a microprocessor, where you have everything kind of in wires and so on. So the question is, can you use that effect? Can you use those interference effects to actually do computations? Well, it turns out there's a very specific kind of computation that can be done rather easily with that, which is a so-called Fourier transform. And let's see, the basic idea of a Fourier transform is this. If you have a signal, like, for example, let's say it's me speaking, there's a certain intensity of sound as a function of time associated with me speaking. Like if I say, if I go, P, and then I stop, and then I go P again. Every time I say P, there's this peak of intensity in the sound. If I there's the one that's kind of the intent well, we can look at the amplitude. If we imagine that it's either my vocal tract, or if it was a speaker on a computer, there's the kind of cone of the loudspeaker, and it's moving in and out, and every time it moves in and out, it's producing a vibration in the air. That's what you hear as sound. So the there's sort of the motion of the speaker cone, and you can kind of plot out the motion of the speaker cone. And in these times when there's an intensity of sound, you'll see there's lots of motion in the speaker cone, and when there's no intensity in the sound, the speaker cone is not moving. Okay, so you can sort of plot the displacement of the speaker cone as a function of time. Okay, so now that's what happens sort of in the sound amplitude as a function of time. The other thing you can look at is to think about the sound in terms of frequencies. So, for example, if you have a pure tone, just something which is at a certain frequency, like, for example, in a first approximation, a middle A on a piano is 440 hertz, 440 vibrations per second, and that is not quite this, because a piano has more complicated kind of character of its sound. But roughly, it's just if you played that through a computer, you would have the sort of speaker cone will be kind of moving in and out repeatedly 440 times a second, and you would get this kind of sine wave that just wiggles up and down. So that's a kind of a pure tone. That pure tone is at a single frequency. So a big fact realized by a chap called Joseph Fourier in the mid-1800s is that you can take any signal as a function of time, and you can represent it by a sum of signals that are sort of pure tones at different frequencies. So the there's always two ways to represent something like sound. It's either as a function of time, so-called time domain, or it's as a function of frequency, so-called frequency domain. And you could say of this thing that I'm saying, for example, you could either say, oh, it's this sound amplitude at this time, and a millisecond later it's a different amplitude, and so on. Or you could say it's a combination of these frequencies at that is, this amount of 440 hertz, this amount of 450 hertz, this amount of something else. Those are equivalent ways to represent that signal. And so Fourier transform converts between those ways of representing a signal. And often when you see speech sounds, for example, you'll see them represented as a spectrogram, which is a little bit of a combination of these two things. It shows you at sort of in little bins of time, it shows you what the intensity of different frequencies is at that bin of time. So it's not showing you, it wouldn't make any sense to say, what's the frequency instantaneously here? You can't determine the frequency. If you just say, if all you know is what the amplitude was at a single time, that doesn't determine frequency, because the frequency is what's happening over time. This is this sort of trade-off between, you can either measure sort of things at a particular time, or you can measure for a longer time and sort of localize the frequency more. The longer you measure for, the more you can localize the frequency. That trade-off between sort of measuring things more accurately in frequency and more accurately in time is the same phenomenon as gives one the uncertainty principle in quantum mechanics. But it's the sampling theorem in signals and so on. It's that you can determine one thing. There's a trade-off between determining the frequency and determining the localization in time. In any case, that's a long way of saying this phenomenon of this thing where you're converting from frequency to from time domain to frequency domain. That's a Fourier transform. Frequency domain to time domain is an inverse Fourier transform. That operation happens to be really easy to do with interference from light. Actually, it's the thing that happens when you make a hologram. You're in a hologram, you're essentially picking up the information about frequency okay, so how does this work? In a hologram, you're trying to get a representation. So a hologram is something you can make with a laser, typically, that allows you to have sort of a three-dimensional image of some scene. How does the three-dimensional image work? Well, what's happening is that you are reconstructing the exact pattern of light waves that would come from that object that would reach your eye. So, and you're kind of reconstructing in sort of three dimensions where those light waves go, and that is what allows you to kind of move your head around, and you're kind of looking at different parts of those light waves, and so you're seeing the object in 3D. In order to do that, you have to be able to kind of play back not just the intensity of the light, but also it's the full sort of wave character of the light. And this is a little tricky to explain. It has to do with the fact that what matters then at the position of your eye is the angle that the light is coming from. And what matters in sort of the way you've laid out the hologram is the position at a certain distance in that hologram. And the transformation between angle and position is pretty much directly analogous to the transformation between time and frequency. And that's sort of why the Fourier transform shows up in what you actually record in a hologram. So if you look at sort of a hologram and you try and look at it under a microscope or something, and you see all these little places where light is coming through or light isn't coming through, it looks like a total mess. It doesn't look like the sort of original scene, because it essentially is the Fourier transform of the original scene, but that reconstructs the pattern of light waves so that at the position of your eye, even at the position of the hologram, it's a big mess. But at the position of your eye, it ends up reconstructing the light waves that you need to see that particular thing. So if you want to do Fourier transforms, there turns out to be a really sort of efficient way to do that just by using the characteristics of light waves. And there are devices you can make that are pretty much just doing Fourier transforms. Given Fourier transforms are sort of your primitive to work with, there are some number of operations that you can do by sort of combining those. But that's Fourier transforms are, among other things, they're linear operations. So I mentioned that one of the challenges is, can you make a switch? Fourier transforms don't help you in making a switch. So that's kind of that story. Now, why would things with photons be more efficient than things with electrons? Well, one of the reasons is that photons go faster, at least in a vacuum, than electrons go in a wire. And so that helps you in making a device that can go faster. And there are effects. Now, when you're dealing with electrons, there are and you have two sort of wires, and they both got electrons in them. There's a certain amount of sort of crosstalk between those wires that comes about because the electrons produce electric fields and magnetic fields as they move through these wires, and that can affect electrons in sort of a neighboring wire. And I guess there's no directly analogous, well, not that in a first approximation, there's no directly analogous effect for light. Because light is not itself a source of light in some sense, unlike, for example, a gravitational wave, which is in a sense a source of gravitational waves. For light, as I mentioned before, the sort of source is the motion of charges, and the actual light wave is just its own thing, doing its thing, and not producing more light waves, so to speak. That same kind of crosstalk effect doesn't happen there. So just a few thoughts on photonic optical computers. Let's see. Oh my gosh, all kinds of questions here. Okay, here's a really different one from memes. Platonic solids have fascinated us for years. Do you think the exploration of four-dimensional hyper-Platonic solids may be useful? So just a refresher on Platonic solids. These were known in antiquity, notably to Plato. And the question is, if you're making a solid polyhedron and you want every face to be the same, what kinds of polyhedra can you make? In 2 dimensions, if you want every analog of a face, just an edge, to be the same, you can make a polygon with any number of sides. You can make a triangle, you can make a square, you can make a pentagon, you can make a hexagon, you can make a polygon, a regular polygon, with any number of identical sides. In 3 dimensions, if you want the faces to be identical, there are only 5 ways you can do that. You can make a tetrahedron where every face is a triangle. You can make a cube where every face is a square. You can make an octahedron where there are 8 faces, they're all triangles. You can make a dodecahedron with 12 faces, each of them a pentagon. And you can make an icosahedron with 20 faces, each of them a triangle. And there are no different choices there are no other ways to take identical faces that are regular polygons and sort of attach them together and make them close up as an object in 3-dimensional space. So, for example, if you were to say, well, gosh, why isn't there a Platonic solid where every face is a hexagon? Well, the reason is the same reason that you can have hexagonal bathroom tilings, so to speak. When you lay out a bunch of hexagons, they just are flat. They don't curl up into a thing that makes a solid. So if you say, I really want a pentagonal, bathroom tiling, so to speak, with regular pentagons, you can't do that, because with regular pentagons, they don't lay flat like that. Instead, they sort of have to be curled up. And when they curl up, they form a dodecahedron. And so, for example, in a soccer ball, you're mixing hexagonal faces with pentagonal faces to make something that is not as closed up as a dodecahedron, but not as flat as a hexagonal tiling. So as I say, in 3 dimensions, there are exactly 5 Platonic solids. In Euclid's work on sort of proving things in geometry, turns out the theorem that takes the longest to prove, his sort of pinnacle theorem, is the theorem that there are exactly 5 Platonic solids. And he was able to prove that in antiquity, and that fact was known to Plato and so on as well. So if you go to 4 dimensions, it turns out there are a different collection of solids. There are, in that case of regular polyhedra, they're usually called polytopes because they're just as in 3 dimensions there are faces of a polyhedron are polygons, and in a sense the faces of a polygon are the edges. Well, when you go to 4 dimensions, the faces of a polytope are polyhedra, and then the faces of the polyhedra are polygons, and so on and so on. So in 4 dimensions, they're usually called polytopes. 4 dimensions and above, they're usually called polytopes, and their faces are the lower dimensional kind of analogous regular objects. So in 4 dimensions, there are some additional kinds of regular polytopes. There's a so-called 120 cell, there's a 60 cell. A cell is the analogous word that is like the word face in 3 dimensions. A cell is kind of the 3-dimensional face of a 4-dimensional polytope. So as you look at different numbers of dimensions, there are 5 regular polytopes, which happen to be polyhedra in 3 dimensions. There are slightly more, I think, in 4 dimensions. I'm forgetting. But the most notable one is the 120 cell. It has the largest number of distinct sort of face-like things in it. Now, as you go up to higher dimensions, you'll get different numbers of regular polytopes. I think it peaks, I don't remember, maybe 8 dimensions, something like that. It peaks in some modest number of dimensions, and then when you go on going out and trying to match up all the conditions to get some regular polytope, the things that eventually that always match are the generalization of a tetrahedron and the generalization of a cube. The generalization of a tetrahedron is usually called a simplex, and you can make those in any number of dimensions. You kind of see why. Well, actually, let's do the cube because the cube is easier. Again, you can get a hypercube in any number of dimensions, and essentially what you're doing is you're going in every coordinate direction. So if you are in 4 dimensions, for example, there are 4 coordinate directions that you can move in rather than the 3 in 3 dimensions. And so you're taking all those coordinate directions, you're starting from one point and you're moving 1 unit, let's say, in each one of the directions, in 4 dimensions, each one of the 4 possible directions. And the things you get to by moving up to 1 unit in every direction, those are like the corners of the cube, or in the case of 4 dimensions, the 4-dimensional cube, the hypercube, often called the tesseract in 4 dimensions. And so that gives you the number of places you get to. So let's see, in the case of a square, there are 4 corners of a square. In the case of a cube, there are 8 corners of a cube, and in the case of a tesseract, a 4-dimensional cube, you're going along each. Let me think. That would be it should be 2 to the n. Am I getting this wrong? It's 2, it's 4, it's 8. Yes, it's 2 to the n. It's for every time you add a dimension, you're multiplying by 2 the number of corners that the object has. So in the tesseract then has 16 corners, so to speak, and you're filling it in like a cube, and that you can keep on doing that in any number of dimensions. You get an object that is a hypercube. You can also get a simplex by instead of filling out sort of instead of allowing yourself to go, so in a cube, for example, the corners of a cube have coordinates that are things like 0, 1, 0 or 1, 0, 0, all combinations of ones and zeros of length, well, n if you're in n dimensions, all combinations of sequences of ones and zeros are possible coordinate positions for the corners of a hypercube. So there are 2 to the n of those because each position is either 0 or 1, and there are n positions, so there's 2 to the n possibilities. In the case of a simplex, you're doing the same thing, but you're only having 1, 1 there. And the others, is that right? Is it 1, 1, 2 ones? Anyway, it's a limited number of ones. And that gives you these kind of slanted faces. You don't get to sort of have the diagonal corner of the cube. So, any case, those exist. The dual of a tetrahedron, which is an octahedron in 3D, the analog of that exists in any number of dimensions. So, does one care about these higher dimensional objects, these higher dimensional polytopes? There are a number of applications for these things. Sometimes they're useful as a way to kind of define how you kind of can move data around in an optimal fashion. They're kind of switching networks that are based on these kinds of things. They're also, they have, that's one use. I don't know of too many. I mean, that's the most common, that's the one that most comes to mind for me. In mathematics, there are a bunch of uses to do with understanding group theory and so on that show up. And you can also ask questions like, well, here's an example of a question. How well can you approximate a sphere or a hypersphere by a polytope, by a regular polytope, a polytope where all the faces are the same? So in 2 dimensions, you've got, a triangle, a square, a pentagon, a heptagon, a hexagon, a heptagon, etc. By the time you've got, a 1,000-sided regular polygon, you've got a pretty good approximation to a circle. So in 2 dimensions, pretty easy to approximate a circle, but with a polygon. In 3 dimensions, the best you're going to get to approximate a sphere is an icosahedron or a dodecahedron, depending on how you're doing the approximation. You don't get to make to make a sort of soccer ball that more closely approximates a sphere. You have to make something that isn't like a regular polytope. You have to have something where you're mixing pentagonal faces and hexagonal faces in that case. So it's an interesting question how well you can approximate a sphere with polytopes in different numbers of dimensions. And that's kind of an interesting issue because that then relates to, it relates to a variety of things about, it relates to some things about error correcting codes, and it also relates to things where you're making discrete approximations to kind of continuous systems where you can rotate in any direction. When you make a discrete approximation, you need something where you can just have elements, for example, on the corners of a regular polytope. Maybe I'll explain that comment about error correcting codes. So we're a little bit off the future question, but maybe I'll explain something about error correcting codes anyway. So the issue is you are trying to send a message and you're sending a sequence of numbers, let's say 7, 5, 8, 2, 4, 6, whatever. And let's say you represent those numbers. Let's say you're representing numbers from 0 to 7. You can do that with 3 binary bits. 0, 0, 0 for 0, and then 0, 0, 1, et cetera, up to 1, 1, 1, which is the binary for 7. Okay, so if all you're doing is to send those bits, then anytime there's a bit that's wrong, if, for example, you thought you were sending 1, 0, 0, but actually you sent 1, 0, 1, that will you thought you were sending a 4, but actually you'll get a 5. So if you're just sending the raw bits, anytime there's a single bit error, there's a mistake that's been made. Well, there's this concept of error correcting codes, where what you do is to, let's say, add a bit. And then what can happen is that that gives you sort of more redundancy. And then you can say, well, if I get either this sequence of bits or that sequence of bits, then I know that really means a 4. And so you're using a certain number of extra bits to represent kind of error correction. Now, the way error correction is usually done, instead of correcting every single number you're sending over, you're correcting blocks of numbers, and you're sort of adding some error correction to that whole block of numbers, and you're adding error correction that can correct, let's say, up to a 1-bit error in this whole collection of numbers. And so that's kind of the approach to doing error correction. And you see error correction, for example, if you look at the ISBN numbers on books, there'll be a 1-2752 dash blah 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 dash blah blah blah. In that case, the last digit is a check digit, I guess, which is sort of the junior version of error correction, is just to know that there was a mistake. It turns out the mathematics of these things works much better when the base of the numbers is a prime. And so that's why in ISBN numbers, you'll sometimes see an X there as well as all the numbers, because it's being done in base 11, because 11 is a prime, and the X represents the digit 10 in base 11. So in any case, error correcting codes. So there are all kinds of different schemes for making error correcting codes, all kinds of different ways that you can add those extra bits to be able to detect errors, be able to correct errors, and so on. Well, turns out a way to think about what's going on is in terms of spheres in high-dimensional space. So the way to think about it is, if you've got some sequence, 1, 0, 1, 1, 1, whatever, you can think about that as a coordinate position if you've got n digits, you can think about that as a coordinate position in n-dimensional space. And every one of those, you're kind of asking that every possible thing you might send is a position in n-dimensional space. So you've got all these different things, 1, 0, 0, 1, 0, 1, all that kind of thing. They're all positions in n-dimensional space. And if you make a 1-bit change, it's like moving if you make any one of the possible 1-bit changes, it's kind of like moving a certain direction, but you don't know what the direction is. And if you're moving a certain amount in some direction, but it's sort of equal what happens in all directions, it's like having a sphere in n-dimensional space. So the problem of error correcting codes ends up being, how do you arrange the kind of code words, the ways you represent these different things you're trying to send? How do you represent those so that if you make a 1-bit change, you're least likely to interfere with another code word, with a code word that's representing a different number, let's say. And so that problem becomes a problem of sphere packing in high-dimensional space, because every code word is a point in in your n-dimensional space, and the error, sort of a 1-bit error, for example, corresponds to a sphere around that point. That what's in that sphere are sequences that you can reach by making a 1-bit error from the original code word you had. So the problem of error correction, of finding error correcting codes, if you want a length n error correcting code, you're dealing with essentially sphere packing in n-dimensional space. And turns out that there's all kinds of cool things that happen with sphere packing in n-dimensional space. And there are certain dimensions, like 26, for example, where it turns out to be possible to have this kind of lattice where you pack spheres in this kind of regular array, hyperspheres in this regular array, and they pack really, really well. In 2 dimensions, when you're packing circles, the best packing is a hexagonal packing, where you're just sort of making where the arrangement of the centers of the circles, if you get a bunch of coins, you just smoosh them together, they'll form this, if they're the same size coins, they'll form this kind of hexagonal array. And that's the closest packing in 2 dimensions. In 3 dimensions, it was guessed by Kepler that the closest packing is the one you often see in grocery stores, where you kind of have this packing of spheres. Spherical fruit is typically packed that way. Let's see, in that case, so in 2 dimensions, the number of neighbors of a circle that's optimally packed is 6. In 3 dimensions, the number of neighbors is 12, I think, for the optimal packing. And the sort of in 2 dimensions, the optimal shape is yeah, this is tricky, but the optimal shape, the sort of region around every circle is a hexagon. In 3 dimensions, I think it's a tetrachedecadon, which is a 14. Is that right? Which is a 14-faced object. And that's a tricky thing because there's this thing, it's called the kissing number, which is the number of points where the spheres actually touch, where and that's a different number than the size of the number of faces in the polytope that encloses each sphere. But roughly, there's in 3 dimensions, only proved about 20 years ago now that packing, sort of the regular packing that you see with fruit in grocery stores and so on, is in fact the best packing that you can get in 3 dimensions. But when you go to higher dimensions, some dimensions it's known what the closest packing is, some it isn't. There's some dimensions where, for weird reasons of the way that numbers line up and so on, you end up with these very dense packings, very good ways to pack things, but only in that number of dimensions. And so those are cases where you can get good error correcting codes where the code words are like length 26, for example. And there's sort of a close relation between the mathematics of those kinds of codes, the mathematics of finite groups, the mathematics of sphere packing, and so on. These are all very related kinds of things. So I think the question was, are there applications of higher dimensional kind of polytopes, regular polytopes? And so I'm sort of giving you a first approximation to that. I think these optimal lattices don't involve regular polytopes. I think they involve different shapes, as I think they even do in 3 dimensions. So it's related, but not quite the same thing. Let's see. Let's see. Well, a couple of questions here. There's one. Okay, there's one from Latch here. Do you think there'll be in the short to medium term future an AI architecture that manages to synthesize mental images to the level most humans do, mainly visual-spatial? I don't know. I think the generative AI systems that are trained from billions of human images and that synthesize, that go from text to images, do a pretty reasonable first approximation job of making kind of realistic scenes of the kind that we see. Now, the thing that's sort of coming is being able to not only make realistic 2-dimensional scenes, but making realistic 3-dimensional objects, and then making realistic kind of video of things that happen with those objects in the world. And there's sort of a big trade-off between whether you kind of learn the trajectory of balls just as a sort of black box thing where you don't really know how it works, or whether you use the physics, which we know, that says that balls go in a roughly parabolic trajectory and they have certain equations of motion, whether you're sort of calculating the physics or whether you're just doing the kind of off the top of your head type physics, and sort of remembering how the physics works in something like the neural net. And that's still not clear whether it is decently economical to sort of just learn the physics in the neural net, or whether it's better to actually do some computation of what's happening. Now, of course, we humans aren't doing a lot of computation about what happens. And we just sort of remember, well, roughly, what you throw up comes down again. Did it follow the exact right trajectory, all that kind of thing? We probably don't really know. We can't figure that out, and nor will the neural nets easily be able to figure that out. So there'll be cases where kind of you have to do the physics to know what will happen. Now, of course, it's a tricky thing because, like in movies, people make visual effects where they make explosions and things, and people can go to a lot of trouble to do the fluid dynamics exactly correctly to get an explosion that really works the right way in this kind of confined space with this feature and that feature. And people will look at it as a movie and they'll say, that doesn't look right. Because yes, the physics was done right, but people are not familiar with seeing that kind of physical situation. I mean, most famously in the movie Interstellar, my friend Kip Thorne carefully actually used our technology to simulate kind of a black hole. And the problem was that a black hole correctly simulated with all the effects of general relativity and so on looks really squished in the case of relevance, the movie Interstellar. But who wants to see a pancaked black hole? Nobody would think that was a black hole. So the physics had to be sort of faked backwards for the sake of having something which people would recognize, oh, that looks like a black hole. So I think these sort of physically accurate things, there are cases where when what you're trying to do is make something where you can really work out what happens, then you need the physically accurate simulation, where it's just like, does it look roughly right? Maybe it's perfectly adequate to use this sort of learned black box physics. But I think those are, I think we have coming pretty soon kind of technology that lets one get sort of three-dimensional, simulated three-dimensional configurations. It's kind of things like text to CAD, text to computer-aided design is certainly something very much coming. Text to sort of 3D objects is coming. You give a description and then there's sort of a synthesized 3D image. And then to video, there have been demos of that for the last year or two. They're slowly getting better, and they'll surely get even better. I think I think when we say, well, what kind of mental images do we humans synthesize? I don't know. I couldn't really, I get, I can imagine images, but if I say, what exactly am I seeing pixel wise? I absolutely couldn't tell you that. And I'm not sure that at the level that we are thinking of mental images, that we actually could describe them at the level of pixels. Now, if you say to somebody, well, paint the thing you're thinking, I'm pretty bad at painting things, but if you were better at painting things, you might be able to sort of take that mental image and produce a painting of it. But my guess is you're filling in a lot of that painting. It's not based on sort of you having a pixel by pixel knowledge of what that image is supposed to be like. It's, in a sense, the way that we get to see images from AIs is a bit different from the way that we see them in our mind's eye, so to speak. I mean, in our mind's eye, my guess is that we are sort of thinking of higher level pieces of images. And if somebody asked us, well, what does it look like? We would describe it in terms of that low level image form, but that's not how we're thinking about those kinds of things. Let's see. Jamie asks, have I come across synthetic biology? Oh, yes, definitely. Biological computer chips and so on. What's my opinion about such fields in science in the future? Well, let's be clear. Synthetic biology is mostly not about biological computer chips. Synthetic biology is about making organisms or things like organisms where you are designing the organism, you're designing the DNA, and you're using the machinery of life as we currently know it. Typically, you're using the machinery of life as we typically know it, but you're reprogramming it to do something different from the life that we currently have. So that's the most common use of the term synthetic biology. The question of what you want that life to do, so to speak, what you want that living system to do, well, that's a different thing. Now, to distinguish that, people usually don't use the term synthetic biology to represent what is an absolutely sort of broad thing that's done in medical research, which is trying to create drugs that have particular actions. A drug is a molecule, and what you are typically trying to do in designing drugs, so to speak, is to produce a molecule that has the right shape to fit into some other molecule that already exists in the body, to block something that's happening in that other molecule, to enhance the effect on that other molecule, and so on. And most of what's involved there is literally the shape of the molecule. And the molecule is, well, it depends what type of, sometimes it's a small molecule that's just something that doesn't really need life to make it. And sometimes it's a protein molecule that is the kind of thing that life churns out all the time, so to speak, that's made from amino acid units. It's a sequence of amino acid units, and it could be a sequence from anything from a few to well, a million maybe. That's kind of pushing it, but on the order of a million of those amino acid units. And the big thing is that proteins fold up. That thing that was a linear chain of amino acids, it folds itself. The way it folds depends on kind of the forces of attraction between different parts of the molecule and so on. Some of them, for example, are hydrophobic. They tend to sort of expel water. Some of them are hydrophilic. They tend to be sort of pulling themselves closer to water. That's one effect. But the general problem of folding a protein is a difficult problem. For a long time, it was sort of a classic, we don't know how to do this type problem. Then in recent times, there are machine learning methods that do a pretty decent job of folding proteins. They do a better job if there have been proteins that have already been seen before, where it's known how they folded, and the machine learning can kind of say, well, it's more or less like this protein we've seen before, so it must fold this way. If you feed it kind of a random sequence of amino acids, typically modern machine learning methods do not do well at correctly folding that protein. It's a tricky business because what does it even mean to fold the protein? Because the protein may not fold in a particular way. It may flop around when it's, for example, in water, which is the way proteins are usually found in the body and so on. But anyway, so there's a giant kind of an effort to design molecules, sometimes proteins, sometimes other molecules that have particular shapes, have particular charge distributions. Anyway, just fit in certain ways to the molecules that we have in our bodies. And that's usually not, I think, referred to as synthetic biology. Synthetic biology is more, let's make a thing that is its own kind of almost freestanding organism that can do something useful. So people have tried at various times, make an organism that will make gasoline, for example. That turns out to be pretty hard because as soon as it's made some gasoline, the gasoline kills the organism and it doesn't go on making it. But there are all sorts of I mean that tends to be the question, and sort of there are questions like what's the minimum length of DNA you need to make a viable organism? If you were running the origin of life again, might you be able to get, even with the same chemistry that we have, might you be able to get sort of more efficient organisms? Because, all organisms on Earth right now, you can trace back to a common ancestor, maybe 2.5 billion years ago, I think. The last universal common ancestor, Luca, is something which is sort of all organisms on Earth today are derived from that organism. And that organism probably had some bad design choices in it, which we've inherited throughout the history of life on Earth. And there's a sort of a question, could you design a better organism, so to speak, from which you could get things like the life that's appeared on Earth? And there's a lot of, I mean, it's a bit disappointing so far because an awful lot of the mechanisms that we end up using for all kinds of purposes are actually things that evolved naturally in biological evolution, whether it's the nanopore mechanism for reading out DNA, whether it's the CRISPR mechanism for editing DNA. A whole bunch of these kinds of mechanisms were things that already existed in bacteria or whatever else, and we just had to find them. They emerged from the history of biological evolution. The let's design something from scratch is something that is something that has not been as successful so far. People keep on hoping that it's really going to be successful. You're going to be able to sort of make a designer organism where you design everything from scratch, but that's proved fairly difficult. And there are places where, there are a bunch of places where one would like to do that, but it's fairly difficult. The simpler case is designing these individual molecules for things like drugs, but already that's really difficult. And there've been a series of times in the past where people have said, we finally got it. We're going to have a way to design drugs and they're going to just work. And it keeps on not panning out. And the latest hope is that sort of generative AI methods will again allow one to sort of have designer drugs, designer molecules that one can use for drugs that where you just have to say, I want something that binds to this particular shape and encloses a manganese atom or something like this, and that somehow one will synthesize, just as one can synthesize an image of a dog or something with generative AI, that one can synthesize a viable sort of protein that will work that way. But that's still something that hasn't become easy to do. I mean, there's a different issue, which is biological computer chips. Yes, there are people trying. I was just saw a demo of one of these a couple of weeks ago of making things like brain organoids, where you actually are making a cluster of even human nerve cells. They don't form in quite the nice organized way that they do in our actual brains. They're a bit more of a mess in the way that they're made from stem cells and so on, sort of artificially. But getting that kind of thing, and and this is not what's usually called synthetic biology. This is a different branch of sort of development where you're trying to get sort of an analog of an actual brain to do computation. And so far, that's really just starting out. I mean, that's really there's very little has been done in that direction. Whether that's a fruitful direction is unclear. It really depends on whether when we make an artificial neural net in an LLM or something, a large language model or something like this, are we capturing the essence of what's going on in brains in a way that is suitable for computers, and it's just that's the right way to do it? Or is there something going on in brains that is something very special, very kind of more advanced physics or something than we are capturing in LLMs? My own strong guess is that there's nothing more elaborate going on in brains. There's a lot more stuff that brains have to do because they need to have living cells that get, supplied with glucose and that send out waste products and all that kind of thing. It's a much more complicated setup. And by the way, they were not designed by an engineer. That what we have in our brains was the result of a few billion years of biological evolution, just trying different things and finding something that worked and then going with it. Even though there may be many, many different things that work, and even though the details of how something works may be pretty arbitrary. I mean, it's kind of I sort of in a sense it's a feature of learning biology that you are in a sense learning all these details of how things happened to be. You're learning the historical accidents that happened in the history of life on Earth. And if you say, well, why is it like that? There's probably no answer to that in most cases. It's like that because, 2.5 billion years ago, this particular random thing happened that caused this organism to go in this direction and this mutation occurred and that one worked out. And so now that becomes a page in the biology textbook, so to speak. And it's not something where you can say, let me drill down and say, why does this fundamentally work this way? It isn't a thing of that character. It's more like a kind of learning. I mean, if you ask about history, you can have some explanation about, well, this happened in history because, so and so got mad about this. And so they decided to have a big, to do some big thing about it. But that's a sort of a frozen historical accident. You can't derive from first principles that was what happened. And I think, in any case, yeah. So there's this question of sort of, is there more if we make a sort of an actual neural network with like human nerve cells? Do we get more than we get by using electronics? Remember, human nerve cells are really slow compared to electronics. They're 1 million times slower than electronics. So there's got to be something really important that you get for it to be worthwhile to go over from electronics. Now, right now, there are things that brains do that artificial neural networks don't do. One of the most notable is, as we think, we also learn. For an artificial neural net, what typically happens is there's a training phase where you try and get the artificial neural net to go from the training data that you have, pictures or text from the web or something like this, and you try and get it to be able to successfully able to do things like predict next words and things in that text. After that training phase is over, which for a big LLM can be a very expensive process, then it's like, okay, we've got this fixed neural net. Now run the neural net, do the thinking, do the so-called inference phase of using the neural net, and just keep doing that over and over again, and do it every time you talk to ChatGPT or every time you're running our notebook assistant or any of those kinds of LLM type tasks. And I think so for neural nets as they are right now, those two things are separated. It's not continuously learning from what you're doing with it, whereas our brains continuously learn as well as while we're thinking, so to speak. It isn't quite known how to do that. There are ideas about how to combine those steps, hasn't quite happened yet. I think that's one thing. The other thing is that our brains use 50 watts. A lot of, for example, training is using a lot more than that. Well, I don't know quite how you compare it, but it seems that brains are comparatively energy efficient, although they do run really slowly relative to electronics. And again, I don't know to what extent that's, how that really works. Another thing is, what's the memory capacity of, this small volume of stuff as compared to the corresponding density of memory in solid state electronics or something. I don't know. I don't know how much we remember. I mean, we have about 100 billion neurons. We have, maybe 10 trillion connections, maybe a bit more than that between those neurons. If each connection is associated with, has information about sort of how strong the connection is, analogous to the weights in an artificial neural net, then it's really pretty disappointing how small the amount of memory we have. It's in the terabyte range. It's the kind of thing you can get on a little tiny thumb drive these days. So we're not, in terms of volume efficiency, if that's how we're storing our information, and there isn't some more molecular scale kind of thing that's storing much more information, then we're not really winning from that point of view either. I mean, I think people were saying, I remember a contrarian chap I used to know named Freeman Dyson, who would make many contrarian statements, was always, computers are going to lose. It's going to be kind of artificial organisms all the way down, so to speak. Well, that certainly hasn't panned out as of now. In the end, there will be more happening on sort of a molecular scale, because computers, I was mentioning earlier, every bit is about 100,000 electrons. And you could imagine a world in which sort of every bit is just one electron. You could imagine something where where instead of these sort of channels in semiconductors, you're dealing with sort of individual molecular processes. In a sense, biology is doing that. The more we learn about how biology works at a molecular scale, the more we realize it's all very orchestrated. When a muscle is moving, it's moving because there's this little thing that is, in a sense, a little ratchet that's going down a long protein, sort of attaching itself the next place, the next place, the next place. It's a thing where there's more machinery, there's more kind of mechanism that we discover all the time, and the cytoskeleton, the kind of the sort of skeletal structure inside individual cells is doing all kinds of complicated things, most of which isn't yet understood. So, there's stuff happening at a molecular scale, and biology is kind of the far out winner of how sophisticated the stuff that's happening at a molecular scale is. And so there's certainly room to grow in terms of what we can do at a molecular scale. Whether we have to piggyback on biology as biology has evolved over the last few billion years, or whether we get to sort of do the engineering from scratch is not clear. I mean, there was an effort to, for example, do computing with DNA, where you're kind of letting the DNA strands line up, and you're kind of doing something where you're making, for example, a tiling, like you have tiles where, the red side of one tile has to line up with the red side of another tile. You generalize that a lot, and you say the tile that has this particular DNA sequence on one side must line up with the tile that has this particular complementary DNA sequence on the other side. And you can use that to sort of build up these patterns of tiles to have a particular form. And that seemed like a good idea. What was it, about 25 years ago? It just turns out, I don't know how practical it is because, by the time you're trying to line up these DNA molecules and things, it's all happening very slowly compared to the speed that sort of switching happens in digital electronics. And one day, I mean, that particular mechanism of using sort of DNA as the working material probably is a very sort of the wrong end of the story, because what we see in actual biology is sort of there is lots of proteins that aren't the whole DNA program, so to speak. They're just individual proteins made from the DNA program that sort of fit together in all these elaborate ways. But it's certainly the case that we can expect that molecular computing in using that is sort of morally similar to what's happening in biology is absolutely going to be a thing that is valuable, because it's just operating at a smaller scale and faster than one gets in digital electronics. Now, having said it's a smaller scale and faster, inevitably that means there are more errors happening. Why are there errors happening? Well, there are errors happening because things are hot. And if it's operating at room temperature, there's that temperature is associated with a certain kinetic energy of all the different molecules that you see in there. And that kinetic energy, things are moving around. And so things that you sort of thought, oh, this is precisely going to line up with this. Well, no, actually, it will get kicked around by the heat that exists, and it won't precisely do that. So then you have a whole adventure of, how does the error correcting code kind of thing work? Or how do you have enough things in there that you're only getting the average, and it doesn't matter that one or two did the wrong thing? And biology has found various solutions to this. Biology does use a few error correcting code-like ideas in the transformation from DNA to amino acids and so on, encoding these different. There are 3 base pairs on DNA. Each one has 4 possible configurations, so that's 4 cubed different possibilities. But there are only 20 amino acids, plus there's some start-stop type signals, and so there's a certain amount of sort of correction in the fact that you can have slightly different sort of base pairs and end up with the same amino acid, at least up to a point. It's so these, as you get really small, really molecular scale, you do have to expect that you do a certain amount of error correction. That's been a big thing in efforts to make sort of quantum computers. I've probably talked about quantum computers a bunch of times. I'm kind of a skeptic on the fact that there's something magic to achieve there. But one of the things is, as soon as you're dealing with, for example, individual photons or individual atoms, there is all kinds of error correction that has to happen. And that's true also, well, it's a longer story about the way that quantum mechanics works. But that's a thing you can expect to have when you get things at a molecular scale. Well, let's see. Okay, I think I should wrap up in a moment here, but I see Spare Parts asking, do you think training AI for generative video will end up with an internal model of physics? I don't know. Insofar as our brains have an internal model of physics, sort of yes. But to say that it's a model is to say that we can convert it into a narrative that we can understand. And the fact that there is some pattern of nerve firings whenever I'm trying to imagine, is this thing going to move in this direction or in that direction? It's not really a model in the usual sense of a model, because it's just this black box thing that has all these nerve firings that somehow manage to come out with the right conclusion. A model usually means that you've taken something that happens in the natural world and you've managed to kind of compress it to the point where there's a narrative that you can kind of fit into a finite mind like ours to explain what's going on. And so I'm very dubious that one will be able to go from a neural net, here's a trained neural net, pick it up and dissect it and tell us what model it has. I don't think that's going to work any more than it would work to take a human brain and kind of dissect it and say, well, what was its model for how to think about, the mechanics or something like this? I don't think that's going to work. I think it's all sort of encoded in the details of what's happening there, and it's not something which is sort of presented in a narrative form that is suitable to sort of feed to us in this kind of compressed representation that we need. And I should wrap up here and go back to my day job. But thanks, as always, for asking all kinds of interesting questions. I see I didn't get to lots of other questions. And I look forward to going on another time. So thanks very much, and bye for now.